Welcome back. We sort of take a quick detour, not exactly a detour. One of the necessary conditions what you have seen for this deviating, spontaneous deviating to take place was there has to be an active interfacial interaction between the two interfaces of the film. And we argued qualitatively that this happens only if the film is very thin and the nature of van der Waals interaction is attractive. It is time that we look into this aspect a bit more in bit more detail. I also sort of you have trusted me so far by allowing me to tell that the interaction between two surfaces, van der Waals interaction between two surfaces, the scaling is no longer 1 by r to the power 6, but scaling is 1 by d square. So, it is time we look into those aspects. So, let us start from this expression, which is the potential energy of interaction between two molecules due to van der Waals interaction is, I am just replacing r with x. So, this is x now, which is fine. In fact, this expression does not even capture the repulsive part. Typically, there is a stiff bond repulsion. This is called the bond repulsion, this part. Very close to the, when the two surfaces are very close, and it is sort of given by some zeta x to the power minus 12. So, you see that the scaling is even sort of the exponent is even higher at the denominator. So, when x is very small, this term dominates. When x is bit higher, this term becomes small and this term dominates, and when x becomes bigger, macroscopic scale does not even need to be macroscopic, few micron onwards both the terms go to 0. So, there is no van der Waals force. So, anyway, beta of course is a material dependent constant, and however, the generic nature remains the same, and this phi dash a sort of represents the potential energy of interaction between two molecules. We would like to look into the interaction. Let us try to understand the figure first. Between two blocks of materials d1 and d2, which are separated by a distance d. So, these are the two surfaces, two blocks of thickness d1 and d2, which are separated by distance d. Okay. So, there we go. We consider a single molecule. So, what we know the potential energy of interaction between two single molecules. So, idea is that we will try to find out two molecules present within these two blocks. We know the expression for the interaction between them, and then we will try to integrate in such a way so that our formulation covers the interaction of all molecules present in block 2 with all molecules present in block 1, that in other words it is the interaction between the two blocks. So, let us say we identify these two molecules who has a separation distance of, let us say, x. We also draw a horizontal line from here, draw paper and identify this is the point. We draw a circular ring within the material or block 1. Look into the construction carefully. Of course, you get a very neat version of the construction in the PPT. So, what we have from here to here, it is Z. This, as I already pointed out, is X, and this is zeta. Of course, the width of this block is d zeta. This is y from the center to this, and the width of this block, this the thickness of this ring is dy. I will just quickly redraw this part of the picture. So, you have a ring so the center of which is at a distance zeta, the width is d zeta, this point is y, the width or the thickness is dy, and this point we have identified, the molecule we have identified in block 2 is at a distance z from the surface of block 1. This is very important. The z is from the surface of block 1, it is z, and this particular molecule we have identified on in block 1, the direct separation distance is x. So, I hope now the picture is clear. You can again have a look of the picture here in the PPT, but I just wanted to give you a flavor of how it is constructed, because I always feel that that gives you a better idea. Of course, I will put up all these scanned copies available to you, make it available to you. Okay. So, now let us see what we can do. So, consider the, so what is the volume of the ring? The volume of the ring, it is ring, not the rim you just learnt in duetting. Volume of the ring is dV, it is 2 pi y dy into d zeta. Now, what is the number of molecules present within this ring? So, let us find out the number of molecules present in the unit volume. In an unit volume, one can easily calculate it from Avogadro's number, but I will show it in the most simple way, so that you all understand and you can remember. So, it is essentially numbers per volume what we are going to find out, and this is something that is known. Number per mole is known, that is the Avogadro's number. Mole per unit volume, of course, you can just write it like you multiply the numerator and denominator with mole. So, it becomes like this. So, this becomes Avogadro's number, and this part again you can split up. Numbers per mole, of course, it remains as it is. Mole per mass, and this turns out to be the molecular weight, and further you can split it as mass per volume. So, what is it? It turns out, in fact, Na M1 rho 1, where Na is Avogadro number, m1 and rho 1 are molecular weight and density of material 1. Okay. So, this is known. So, then number of molecules present within the ring is Na by m1 into rho 1 into 2 pi y dy d zeta, based on the figure and the construction we have made, right. Now, what we have is the essentially it is the assumption of additivity, that the total so what we find out at this point is the interaction of one molecule, this is this molecule present in block 2 with all molecules of block 1 present within the ring, right. And what is the total interaction? It is based on the concept of additivity. The net interaction energy between one molecule of phase 2 or block 2 block 2 with all molecules of block 1 within the ring is we do not even use a symbol, we will talk about it later. See, what has been done is very simple. You know the strength of van der Waals interaction between two molecules of 1 and 2 is this beta 1 2 divided by x to the power 6. You have identified, so what you have done is that you are now looking into, so in other words, let me just try to take a minute to explain this. The strength of interaction of this molecule of 2 with one molecule of material 1 is given by this. So, it has the same strength of interaction with all the other molecules present in the ring, right. We are assuming that all the molecules present in the ring are at a distance of x to the power 6, x to the power minus 6 are at a distance of x from this particular molecule. So, what is the total interaction energy of one molecule of 2, that is this molecule, with all molecules of 1 that is present within the ring? You simply calculate the number of molecules present in the ring, multiply with this, and you see that is exactly what we have done. This part corresponds to the ring volume. This is the number of molecules present per unit volume. You multiply that. So, these two, product of these two in fact gives you number of molecules present within the ring element, and this is what you have. So, now based on this, what you can do is you can now find out the identified molecule in block 2 with all molecules of block 1. And how can one do that? One can simply do that by integrating this expression within suitable limits, and what are the expanses of block 1? Zeta stretches from 0 to d1 and y stretches from 0 to infinity. So, you simply perform this integral you need to perform this integral. I think the detailed steps are given here. So, all we need to do, but I will are given in the PPT, but I will do it in front of your eyes so that you can follow it clearly. All we need to do is to invoke the Pythagorean theorem, where we write that we find based on the geometry that x square is in fact z plus zeta whole square plus y square. This is some simple Pythagoras theorem. So, what we have is this, let us write this as some w d, not the phi double dash exactly. So, yeah. So, you see this expression for phi double dash, in fact you can write minus rho 1 n a pi beta 1 2 by m1. Those are in fact nothing but the constants, they are coming out. So, where has this come? In fact, this comes from the expression of you simply get it from here 2y dy, you get this, that is why the 2 comes in and you substitute x in terms of these, right. So, this is simple algebra, just do it yourself. Now, we first look into this part of the integral. And this gives you, in fact, again if you perform this definite integral and integrating. So, this integral, now if you integrate the expression that you have got here, you will get an expression like this. This I just suggest that you sit with it once and just do it. So, this y dy is there, all you have done is, see this part is already there in the expression, all you have done is you have replaced here, how you have got it, if you still have doubt, replaced x in terms of y, z and zeta using Pythagoras theorem. To some of you I am going too slowly, but it is just for your all other friends to catch up, and I always teach like this. These steps often tend to drive away people, but there is nothing to be scared, you should understand every step. So, the expression of phi double dash at this stage, which is not exactly phi double dash, let us write WD, because this is phi double dash we will be using for interaction of all molecules of 2 with 1. So, I will just replace this as WD. Turns out to be minus rho n a pi beta 1 2 divided by 6 m1 this. So, what is this? In fact, This gives the energy of interaction of a single molecule of all molecules of 1. So, now what do? We simply do that, just look into this figure. So, what we have is the, for this block as well, just like this formula, this expression, not even a formula, this is the expression we derived. So, number of molecules per unit volume is simply okay. What we do is we identify a region, cross section is A and the thickness is dz. So, we now know the strength of interaction of all interaction energy of this particular molecule with all molecules of 1. So, what we can do is we can find out the energy of interaction of all molecules present within this thin strip with that of 1 very easily, and that turns out to be, take a fresh page and write it here. What is this? This is simply, you actually need to multiply. So, let us take a minute to write it down. A is, let us say, the cross sectional area. So, this is in fact, this particular term is the number of molecules present within this thread. But what we do is we look at the interaction per unit area, therefore, we divide it by A, and that gives us an expression for GLW. And so, what is the expression for GLW? The expression turns out to be, now you see the limits of Z varies from D to D plus D2. The limits of Z, this is how Z is defined, in fact, Z starts from here. So, the limits of Z varies from D, that is here, to D plus D2. You simply integrate to get the GLW, that is the energy of interaction between two surfaces due to van der Waals forces, and this turns out to be, my suggestion would be what I suggest also when I teach this particular stuff in a class, that do the derivation once. It is very easy, but if you do not do it, you will feel scared and you will also mess up. You will never understand how the terms are coming. So, you can look into what I have done, more than welcome to see it, and then please do the derivation once. So, we take out a constant which is A12, this part we take out. In fact, this pi square is not coming, in fact, we have deliberately made it pi square to look it symmetric with Na square, and 1 pi in fact goes in the denominator, and this is what is known as the Hamarker constant. So, A12 is a Hamarker constant that depends on the densities of the two, or the molecular weight and the densities of the two blocks we are talking about. So, the expression that we get after you perform this integral is GLW as a function of the separation distance is minus A12 divided by 12 pi. Please remember this 12 comes from integral, it has nothing to do with 1 2 we are writing here, and that gives you d1 plus d2 plus d whole square. It is a simple integration, but please do it. D plus d1 whole square minus d plus d2 whole square. So, that is the expression of the van der Waals interaction between two surfaces. I have said that the interaction scales as 1 by d square. Well, it is in fact true. What we have done is we have considered two surfaces of finite thickness. If you now consider that the two blocks are very wide, that both d1 and d2 tends to infinity, then you will find that GLWD between two surfaces, only the two surfaces, actually becomes A12 divided by 12 pi d square at the denominator. So, here you see one thing I have proven, it is a case like this. This stretches to infinity in this direction, this stretches to infinity in this direction, and what you get is the van der Waals interaction between two surfaces scales as 1 by d square. But this expression that we have derived, it might take some time for you to get used to this expression. I earnestly request that you do the derivation once, so that you get a grip on what we have done and you understand it very, very well. Actually reveals something more interesting, because we have considered finite thickness. So, we can in fact plug in the thickness of a film here and we can get an expression of disjoining pressure. That is something that I will take up in the next class. Thank you.